Let's take a moment to talk about the notion of power functions. A power function is any function that's just a variable to a single power. So we only have one term here. But on the other hand, we're allowed to have any exponent p. So with polynomials, we were required to have only whole number exponents. With power functions, we can have any old exponent. And then we also allow them to be composed with anything linear. So here we've got x to some power, multiply by a number, subtract a number, that's no problem. We can also add a number inside, multiply by a number inside, anything we like. And the reason that we can do that is that we know all about how to deal with linear stuff. That's real easy. So in order to actually be able to work with any old power of x, we need to talk about, well, what properties do these things have? So if the exponent is a rational number, so that means 1/3 is in, root 2 is out. If it's a rational number, we'll write it as m over n. Right? So I'm just introducing that notation. And we're always going to write it in lowest terms. We're not going to talk about fractions that are not written in lowest terms. Because if our exponent is a fraction, we already defined this. This is the nth root of x to the m. Or we could write the exponent outside, like that. If our fractions are always written in lowest terms, if the fraction is in lowest terms, then the order on those doesn't matter. Now, if our exponent is irrational, we haven't formally defined that, but I'm going to tell you now that it's a thing. If the exponent is irrational, we only define it for positive numbers x. So x has to be positive. And the reason for that is, with fractional exponents, x to a fractional power may or may not be defined for negative numbers and for 0. And so we don't want to go into those woods with irrational numbers. If our exponent is negative, so remember, if the exponent is negative, this is something like, make the exponent positive and put it in the denominator. So that's undefined at 0. And taking 1 over something, we also never get 0. So we can't have 0 as the input, and we can't have 0 as the output. If p is rational and the numerator is even, then the output is always positive or 0, because we're taking an even power. Remember, if we take an even power of any real number, we can't get a negative number. If n is even, this is the denominator, then our function is defined only for positive numbers or 0, since we're taking an even root. And also an even root is always positive or 0. So this is just pulling together a lot of things that we already know in one place. And all of these facts are what we use to determine the domain and range of a power function. So if we have an irrational power, the domain and range consist of all the positive numbers. If we have a negative exponent, we throw out 0 from the domain and range. If we have a rational exponent with an even numerator, then we have only positive numbers in the range. And if we have an even denominator, well, then we have only positive numbers in the domain and the range. So let's see an example. Let's find the domain and range of x to the negative 5/2. So the exponent is negative 5/2. This is rational. P is negative, so we throw out 0. N, our denominator, is even, so only positive numbers, or 0, but we already threw out 0 here, are in the domain. Also, because n is even, only positive numbers, again, or 0, but we threw those out, are in the range. So the domain is all the positive numbers, that's 0 to infinity. The range is also all the positive numbers, that's 0 to infinity. Now, the main reason that we're concerned with the domain and range here is that our next goal is going to be to say, what kind of an inverse does a function like this have, in order to be able to solve equations in which expressions of this kind appear.